Good morning. My name is Daniele Struppa. I'm the Chancellor at Chapman University, and I'm very pleased to bring a really interesting lecture today. As you all heard, on March 17, the world heard the news of the outcome of a very interesting experiment carried out by an American team on a project called BICEP. The experiment had to do with the detection of signals from the very early universe, the very first fraction of a second after the Big Bang. And we are lucky to have with us an expert in string cosmology whose research actually is connected to this particular research, Professor Nayeri. Professor Nayeri is with our Schmidt College of Science and Technology, and is also a member of the Institute for Quantum Studies here at Chapman University. And today we present a talk with the title Tales of Two Colors, Red versus Blue Tilted Gravitational Waves. Please welcome Professor Nayeri.
Thank you so much, Chancellor Struppa. So as you know, I'm going to talk about an alternative model to what is proposed by inflationary models, which are saying that they can produce gravitational waves, primordial gravitational waves. So, but apparently, according to the data, there is a discrepancy between what inflation predicts and what our model, which is the string theory model, cosmology, is predicting is different than what inflation predicts. So let me go quickly over what cosmology means. So cosmology basically is studying the universe as a whole. So we want to study the big structures, to study about the content of the universe, the fate of the universe, its evolution, its starting point, and its ending. So that is a task of a cosmologist. There are some questions about, important questions about in cosmology. For instance, why only there are 3 spatial dimensions and 1 temporal dimension? How does the Big Bang, the so-called Big Bang, started? And why the universe has these contents that we see right now? So these are important questions, and we're going to try, as an honest cosmologist, to answer these questions. Okay, so as you can see in the picture here, we can say that there was a primordial time right after Big Bang. So there were some quantum fluctuations perhaps produced during the inflationary era. And then those primordial fluctuations made some footprints on the so-called cosmic microwave background. And right now, we are able to observe what is left as the relic of the Big Bang, the initial quantum fluctuations. So as you can see, there is a line here which is basically dividing what theoretician can do here and what we are trying to observe. What is being observed right now, it's the signatures of the primordial gravitational waves, which are extremely interesting. It shows some interesting features about the very, very, very early universe. So again, as you can see in this picture, in this graph, there was an initial inflationary era, and then we had an era which we had a hot soup of plasma, and then that was the last time that the light from the Big Bang actually was scattered from this soup, and then the light was almost left intact until this time. And that's what they have observed. So apparently, the universe has started from a Big Bang. So the problem with the Big Bang is at the beginning, there is a singularity. So this is outcome of Einstein's theory of general relativity. The problem is this theory predicts something which cannot talk about it. Namely, all Einstein equations become singular, infinite. And that's not good. So that's the reason we call this point singularity, and physicists have been trying to resolve this problem. So Big Bang is actually explosion of energy, which all entities in the universe, all beings, galaxies, stars, including us, are outcome of that explosion. So as I mentioned, we want to understand whether we can remove these singularities, this bad behavior functionalities that we are seeing in Einstein's theory of relativity. And so, as I mentioned to you, this scenario means we have a critical ending and a singular beginning. This is all about cosmology. Also, we know that our universe is expanding. So, since we know the universe is expanding, actually, if you rewind the movie of this expansion, you will get to the singular point, which is the Big Bang. So these are important notions that about when the universe was quite young, when it was only 400,000 years old, the universe became transparent. Before that, the universe was opaque. We couldn't see beyond that point. So it's very important to distinguish this 400,000 years. And comparing to the age of the universe, which is about 14 billion years, universe was quite young when it became transparent. So the light that we are seeing is left over from around the time when the universe was only 400,000 years old, and it remained almost intact until it reached to our eyes. So we see this radiation coming from all over points from sky. So it was interesting to see that this radiation is the most perfect blackbody radiation that we can see. Actually, you can see the error bars here. The precision of this blackbody radiation diagram is about, 200 sigma. So this is the accuracy of this blackbody radiation, which is amazing. So it's the most precise blackbody radiation so far we have found in the nature. It is amazing. So as I mentioned to you, this light was scattered from the ions and electrons during the time when the universe was a hot soup of a plasma. So we want to understand the evolution of this light, which has many informations from the very early universe until right now. So our goal is to see how we can provide a solution about the very beginning of the universe. So the universe was much denser, much hotter at the beginning. And of course, as the universe expands, the universe becomes cooler and rarer. So this is a transition that you have from 400,000, when the universe was 400,000 years old, until right now. So this is what we have. Actually, the cosmic microwave background is the most important ingredient in the universe. As Steven Weinberg said, you can, by studying the cosmic microwave background, actually you can understand what God had for his breakfast before creating the universe. There are so much information in the cosmic microwave background. So the cosmic microwave background was observed in 1960s by two American physicists, Penzias and Wilson. And that was a remarkable discovery. They got the Nobel Prize because of that, and they found that the temperature of this radiation that we observe right now, because the universe has been expanded since then, the temperature went down to almost 3 degrees Kelvin. So this is what do you see about the cosmic microwave background? So the universe as a whole, when you look at it from the large scales, it's completely smooth. Okay? It's homogeneous. It's isotropic. This is what you see. But it seems that there are some anisotropies in this cosmic microwave background. And these are important anisotropies due to the quantum fluctuations in the very early universe. Actually, if the universe was smooth, we couldn't be here right now. There should have been some quantum fluctuations left over from the time of the primordial inflation, such that we would be here right now. Okay, so if you include higher orders, you can see to the first order, the universe is homogeneous and isotropic. And then you will see, if you add higher orders, some inhomogeneities in the universe. Actually, the universe is homogeneous to 10 to 1 million. This is extremely, extremely homogenized universe in large scale, which is really, really interesting. But it is also interesting that since we have improved in our technology, starting from the COBE, and then WMAP, and then Planck, and right now BICEP, we have improved a lot in observing smaller and smaller scales. I'm going to show you some pictures which shows how much we have improved in understanding the details of this cosmic microwave background radiation. This is COBE, and then this is 1992. So look at the other picture, which is just WMAP. So the first one also shows a picture of a baby, and that's COBE. And the other one shows a same picture of that baby with WMAP. It shows how much we have improved in having higher resolution in just almost 20 years. So that's what we have right now. This is our actual universe. So this cosmic microwave background radiation shows the initial quantum fluctuations in the universe. So how you can produce these initial fluctuations in the universe? There are different scenarios, different methods that we can provide one of them. Okay, so for instance, one of the very successful ones so far has been cosmic inflation. So what cosmic inflation does is to stretch the universe in such a way that actually the expansion of the universe becomes superluminal. There's a superluminal expansion during this early period of the history of the universe. So if this is the normal expansion of the universe in this graph, you can see that during the inflation model, the universe becomes so large, it's going through a superluminal expansion. So it becomes from a size of close to a Planck to a size of a marble. This is a huge expansion. So the idea was set forward by Alan Guth from MIT. So here, Alan and I were standing on a boat in Paris for the 25th anniversary of inflation. So I was invited for that to give an alternative model to inflation. So inflation was able to precisely give, with a high precision, to predict the initial quantum fluctuations which was compatible with the observation. So what you can observe actually in the sky is by observing the cosmic microwave background, you can go to higher resolution, which means smaller and smaller scales. So this is how the cosmic microwave background will look like when you observe it. So to the first order is just the Planck blackbody radiation, and then you can see other peaks which are called acoustic peaks, and then there are some contributions from other sources, which I'm not going to discuss it right now because that's not my intention for the moment. Okay, so let me switch the gear. We know that there are 4 forces in the nature: gravity, strong and weak nuclear forces, and electromagnetic forces, which describe what is known, the 3 other forces describe the so-called standard model of particle physics. The problem is that we cannot quantize gravity with the other 3 forces unless we have a kind of transition from a particle nature of the, this fundamental particles to string nature. We can have open strings and closed strings. So interestingly, closed strings are responsible for what is known now as gravity. So different vibrations of these closed strings will give us particles like gravitons, which are responsible for gravitational force. Open strings can give us different particles, gauge field particles. So going from particle to string, we have to pay a price. The price is you can unify gravity with the other 3 forces, but the price is now you have to do this in higher dimensions. At least you need 10 dimensions. So that means basically you need 6 extra dimensions. Remember, we are living in 3 plus 1 dimensions, 3 spatial, 1 temporal, so now we need 6 more spatial dimensions. That's the price you have to pay to unify gravity with other forces. But doing so, going to extra dimensions, it provides us more degrees of freedom. So what are those degrees of freedom? This is the transition that I want you to pay attention. There would be vibrational modes, quantum vibrational modes, and also quantum winding numbers. I'm going to talk about these quantum modes, which are extremely important. So the first thing is quantum vibrational modes. So as you can see here, these are the vibrational modes of strings. So different vibrations of string could give you different particles, and that's amazing. These vibrations could go to the left or to the right, and they can be superimposed on each other to provide different particles. But another interesting of these closed strings is what is known as winding numbers, quantum winding numbers. So that means strings can be wound around space. And this is extremely important. So these strings can be wound once, twice, or 10 times, depending on the length of the string. But what this winding does for you is actually 2 interesting features. First, it prevents the expansion of the universe. So if the strings is winding around the space tightly, it prevents expansion of the universe, as if you were tied by tight ropes. So you cannot jiggle or try to move because you have been tied by these strings around you. The same thing here for the space. So if we assume that the universe is flat, but its topology is a little bit different, it still is flat, but it's like a donut, a torus, then strings can go around this space, can be wound around this space. And as far as it is tight around the space, the universe cannot expand. So what does that mean? That means the expansion can happen if strings are loosening up. So here it shows how the expansion can happen. Look at this. So as the strings are loosening up, the universe expands, as you can see. So what does that mean quantum mechanically? It means that you have the annihilation of winding numbers, quantum winding numbers, to momentum quantum numbers. There is another interesting feature about this. This provides you something which is unique to string theory. We have something which is called duality. There is no difference between the big universe and the small universe, as you can see in this clip. The big universe is same as the small universe. So for our universe, there is a dual universe. For each of us here, there is a dual of us in the other universe. Our universe is expanding, the other dual universe is contracting. With this winding quantum number, you can bypass the initial singularity, and which is amazing. So there is no initial singularity. Before you reach the singular point, you will find yourself in the dual universe. So by having this property of strings, you may bypass the initial singularity of the Big Bang. So this is the result. We are dealing with the dual universe. This is called, for some traditional reason, from some historical reason, it's called T-duality. T stands for the target space, but what does that mean? It means there is no difference between the physics of large scales and small scales. And this is an amazing result. Because, first of all, as you can see in this graph, there wouldn't be any initial singularity. Also, it sets a higher maximum temperature to the universe. In the standard Big Bang cosmology, there is no maximum temperature. Actually, the maximum temperature is infinite. That's another singularity in the physics that you have. But with strings, you can prevent reaching the maximum temperature. The infinite temperature. So you do have a maximum temperature here, and the maximum temperature is solely due to finiteness of the vibration modes on the strings, because strings can have only finite oscillatory modes. This maximum temperature, by the way, has a name, and it's called Hagedorn temperature. And it plays extremely important role at the very beginning of the universe. So strings are vibrating. They are thermally vibrating, extremely with high frequency. And that plays important role in what we see for. So in this clip, you see the vibration of closed strings. So you can imagine now you have a universe which is filled with closed strings. So instead of having a gas of particles, you have a gas of closed strings. Now, this closed strings can provide you a thermal fluctuation which can set some footprints on the so-called cosmic microwave background. This is the difference between our model and the inflationary models. Remember, I told you during the inflationary model, which is the graph on the right, the universe undergoes a superluminal expansion. Okay, so that means the quantum fluctuations will go under this exponential expansion. In our case, in our model, the string gas cosmology, which we developed it a few years ago, the universe actually shrinks from a huge size, by huge size comparing to the Planck length, to a size of a millimeter. And there is no exponential growth of these thermal fluctuations. But since the universe shrinks, then there would be an opportunity for these thermal fluctuations to exit the so-called Hubble radius and enter the universe at much later time. These are playing important roles. So this is now, you can see what I mean here. So you have initial thermal fluctuations in this graph you can see. You have initial thermal fluctuations. It's quantum thermal fluctuations, to be more precise. And it is completely different what you can see in inflation models. And then you look at the evolution of these thermal fluctuations to much later time, which will set some imprints on the cosmic microwave background. And this gives us some spectrum, which is called the power spectrum. The power spectrum actually is showing you that if you go from, if you look at your analog radio, if you go from one station to another station, if you hear noises, then it tells you some information. Usually if you go from one station to another station, you feel some noises. Inflation predicts that it shouldn't be any noises, whether you go to higher frequencies or lower frequencies. Just white noises, nothing, okay? So on the other hand, it seems that there is a small bit of tilt in this power spectrum towards the red. What does that mean? That means if you go to lower frequency, higher wavelength, you will hear noises. But if you go to higher frequencies, shorter wavelength, you wouldn't hear any noises. Basically, that's what it means. So inflation predicts a little bit of red tilt. We also predict the same thing as far as you look at only the thermal fluctuations of strings. So far, we have no problem, no discrepancy with the inflationary models. But inflation also predicts that there should be some primordial gravitational waves. So what does gravitational wave do here? They are ripples in the fabric of space-time. And here I have an interesting clip to show you about producing this gravitational waves. So what gravitational waves do, it's, as you can see, it twists the space-time and whatever it's close to it. It can fuse objects, masses together. So this is very important result from gravitational waves. But the problem is that gravitational waves are extremely weak. It is hard to detect them. But it does something to the light at the beginning. It polarizes it. So here people in BICEP 2, in the South Pole, they were trying to find the polarization of the light due to the ripple of the space-time. So the story is very easy. It's basically just because of the scattering, the so-called Thomson scattering. So if you have, this is very important, if you have two spots, cold and hot spots, are now vibrating, they polarizes the light different ways. This will give you a net polarization. But for instance, if you are looking at the particular spot in the universe in which it's surrounded by hot spots or cold spots, you wouldn't see any net polarization. So the only way you can see a net polarization would be that particular spot in the universe would be surrounded by cold and hot spots. And what is the meaning of the cold and hot spots? Hot means they are overdense, or you can see a ripple in the space-time, and the cold means a dip in the space-time. So that's what they have done in the BICEP 2 actually. Look at the polarization of the light coming from different spots, from the cold and the hot spots in the very early universe. So passing a light as a wave, it goes through different regions of space which have some cold and white spots and hot spots, sorry. So cold and hot spots polarize light the same way that you can see the polarization of light, for instance, after the incident, your dashboard in your car. So there could be linear polarization. We have two different polarization. There could be linear polarization. It could be either vertical polarization, for instance, in the case of the cold spots, would be vertical polarization, or horizontal polarization for the hot spots. But there could be another way to produce this polarization, which is due to the circular or elliptical polarization, and that's through the jiggling of space-time, actually. So that means now we can see different modes. There are two different modes that, in the terminology, they call it E modes and B modes. E modes are related to the fluctuations in the energy density, and the B modes are solely due to the gravitational waves. So what BICEP 2 did was observing these B modes, which was the sign for gravitational waves. So this is how you can see the E mode, B mode decomposition. So E modes are coming from the cold spot or the hot spot, and those are either, as I mentioned to you, vertical polarization or the horizontal polarization. While for the B modes, the polarization would be slanted by 45 degrees, for instance. So this is a picture that you can see that there is a pure E polarization, E mode polarization, which is solely due to the scalar perturbations, energy density perturbations in the space. And the other one is due to the gravitational waves. So this is the BICEP 2 project conducted in the South Pole. And they did it very precisely with the precise measurement. And the result is amazing. So they found not only signals in the E modes, but the signals in the B mode. So in these two graphs, you can see the torsion and twists in the cosmic microwave background. Just compare these two graphs, the E modes with the B modes, as you can see. In the E modes, you just see a circular polarization, but in the B modes, you can see this jiggling effect, as I was saying. So what is the result? The result is showing that there are some primordial, as I mentioned to you, if you would be able to measure the B modes, it's a sign for you that there are some primordial gravitational waves. So BICEP 2 is now claiming that there are some initial primordial gravitational waves. So this plot shows the graph of R, which is the ratio of the amplitude of the gravitational waves to scalar modes. And as you can see, it's small, it's 0.2, but it's still significant to claim that there are some initial or primordial gravitational waves. And this would be the imprint on the cosmic microwave background. What is the problem here right now? The problem is that a few years ago, there was a European satellite launched called Planck. Planck didn't see, at least to that precision, they couldn't find any primordial gravitational waves. So that it means there is some tension now between BICEP 2 and the Planck result. And this could be the result of some, ignoring some foreground collapse of stars, because the light was coming through us, and there could be on the way, there would be a collapse of a big star to a neutron star, and that could provide some ripples in space-time. So maybe that's the reason, for instance, they observe a non-zero gravitational waves. So people are kind of skeptical about the result of the BICEP 2 at this moment. But if the tension goes away, and this is, by the way, the result that you can see. So BICEP 2 predicts, or they found, that the gravitational wave would be the ratio of the gravitational waves to the scalar modes, that means the energy density modes, is 0.2, while Planck observed almost nothing, or they said that it should be less than 0.11. So that's the tension for the moment between the two teams, the European team and the American team. We should see who is going to survive. So we predicted, that's the part that we are differing from inflation. Inflation predicted either no tilt in the gravitational waves. Again, remember, tilt means if you go from one station to another station, you will hear noise in higher frequency or lower frequency or nothing. So inflation predicts either no tilt, that means no noise, or at best, they predict red tilt, which means you should hear only noises, or you should observe noises if you go to lower frequencies, longer wavelengths. That's the reason they call it red tilt. So in principle, this is the place that we can set forward an experiment which distinguishes these two models, string gas model and the inflationary scenario. So in inflation predicts a red tilt, string gas predicts a blue tilt. Why? Because the way that we are producing it is different. That's how we produce a gravitational wave. So again, it's the perturbation in the winding of strings. So as you can see, there is a bulge in the torus, which is the background space, and this bulge is moving and twisting. The way that these gravitational waves have been produced provides us a blue tilt. So it's the nature of the Hagedorn phase plus the nature of the winding numbers of strings provides a blue tilt. But why we are excited about this new findings? Because if BICEP 2 is correct, and if their findings is right, then what we're going to see, according to some, so BICEP 2 didn't do these things. But Anthony Lewis plots show, and he's claiming definitely, that the result will show a blue tilt. And if this is the case, we are the winner of this data, because general inflationary models cannot predict red tilt unless there is one way that they can, inflation models do predict red tilt, they cannot predict blue tilts, unless you will lose the Gaussianity, and this is very important. So if these initial quantum fluctuations are non-Gaussian, then you can get a blue tilt. But so far, what we see is these quantum fluctuations are really Gaussian fluctuations. So it is hard. While in the string gas cosmology, there is no non-Gaussianity, and still we are going to get a blue tilt. So if you look at these two plots, it will show a blue tilt, a quite actually large blue tilt. What you see on the right graph is just the result of the bicep 2. On the left one is the combination of the Planck, WMAP, and the bicep and the Keck. It shows that this spectral index for the gravitational waves is towards blue. Well, if this result holds, this would be an amazing, amazing result for string gas cosmology from 2 points of view. First of all, I would be happy with my colleagues because our model is going to fit the data much better than the inflation models. But also, if this is true, perhaps this could be the first signature of a string theory, because people were predicting we cannot test string theory maybe in 200 years from now, but this could be the first signatures of the existence of strings. So in this model, let me conclude. What we have done is we generate a thermal quantum fluctuations with closed strings. And during the Hagedorn phase, the strings are vibrating so much, which provides us the correct red-tilted scalar modes. But also, we are able to produce gravitational waves, but with a blue tilt. So, in future, if they do a more thorough analysis of the data, and they found out that the tilt is blue, and there is no non-Gaussianity in the data, that's going to be the end of the struggle between the red and blue, I would say. So what is left now is inflationary models are very good for predicting the scalar modes and the gravitational modes. There are models based on string theory and even from quantum field theory predicting zero, for instance, gravitational waves. So if this is true, they are ruled out now. Okay? So for instance, the ekpyrotic scenario is being ruled out by this recent data by bicep2, because in the ekpyrotic scenario, there is no primordial gravitational waves. So bicep2 is saying there is primordial gravitational waves. And secondly, if there is a blue tilt, then you cannot get from the general inflationary models a blue tilt unless you are willing to leave the Gaussianity of the initial quantum fluctuations. So that's it. I'm going to end it here. And with that, and wing for blue, I hope that in future the data will show that the tilt is towards the blue rather than red. Thank you for your attention. Okay, it seems that we have a question from Professor Aharonov here.
Comparing the two experiments that disagree, which one has stronger statistics or is more founded? So.
Oh, you mean for the gravitational waves?
Yeah, right.
So for the gravitational waves, the two teams you're talking about, the Planck team and so both of them have good statistics, but the problem is whether each team they did the good amount of their homework.
Cleaning the noise.
Yes. Yeah. So there are foreground noises, and they should be very careful about extracting those foreground noises. So Planck team is claiming that they cannot find any tilt, any gravitational waves actually, and on the other hand, bicep2 is claiming that they found it. So I guess we have to wait a little bit. Many people think this tension will go away, and many people think that depending in which group you are associated with, I know even some people in the WMAP team, like David Spergel, who was very much involved in the WMAP team, which was the American team, they are more favoring the Planck result rather than the bicep2 result. So there is a little bit tension here between the two groups, and I think we have to wait for more data. And you're absolutely right. More data is going to come
in a few months.
In a few months.
Yeah. The only thing I disagree with you, you say there is a little bit of tension. I think there is a very big amount of tension.
Well, that's
Okay.
true, but again, I wanted to be very conservative here, but
Okay.
thank you so much for your
welcome.
excellent questions. Thank you, guys. Thank you.
Okay. Okay, let's thank you.